Hi guys, do you want to compare homework answers with me?
Yeah, sure. What did you
Sure.
get for the first problem?
I solved the first problem by first subtracting over the x values that were not being multiplied by y. I then pulled out the y squared from both terms on the right side and divided by the x values on the right side. This got me y is equal to plus or minus x. To graph this, I just graphed y is equal to x and y is equal to negative x in the same coordinate system. This is what I got for the graph.
I did problem 2, and I used the principle of mathematical induction for the proof. Induction is basically saying that if an equation works for n equals 1 and n equals n plus 1, then that implies it works for all positive integers of n.
How does that work?
You can easily prove that an equation works for n equals 1. So induction is saying that the link between n and n equals 1 works. Once you've proven this link, then you can say that the equation works for all positive integers by induction.
Oh, that makes sense.
Yeah, so for problem 2, I plugged in 1 to the equation, and that produced a positive integer. Then I multiplied both sides by 7 to get n plus 1. And I proved that that will always be a positive integer because a positive integer, n, multiplied by another positive integer, 7, is going to be a positive integer. This means that by induction, 7 to the power of n subtract 1 is divisible by 6.
Yeah, that's what I got too. For problem 3, I used the intermediate value theorem to prove that the sumer is equidistant from point A and point B at some point x. The sumer's path is continuous because you can't just teleport through the water, and point A and point B are at different heights, so the problem satisfies the criteria.
I was confused on how to use the intermediate value theorem though, because I don't know which equation to use.
I'll use the function f of x equals d of ax minus d of bx. That means it's equal to the distance of where the swimmer started to the point x. That's supposed to be in the middle, minus the distance of where the swimmer ended to the point x. To solve where x is in the middle of the swimmer's path, you need to see that set the equation to 0, so the distances are equal. You then plug in a for x and solve. That gets you f of a must be smaller than 0. And when you do the same for f of b, you get that f of b must be greater than 0.
Oh. So then you can use the IDT to determine that there must be a number x in the closed interval a b, where x is equally different from point A and point B.
Yeah, exactly. And problem 4 is really easy. All you have to do is divide both sides by square root x, and that's in brackets k.
No, you got that wrong. Doing that will give the equation infinite solutions.
Yeah, I solved it by setting the two equations equal to each other, since that's where they would have exactly one solution. Then I took the derivative of the equation and isolated it for k, which is 2 square root of x times quantity 2e to the power of 2x. I plugged this in for k in the original equation and found out that x is equal to 1 over 4. Plugging this into our expression for k gives us 2e to the power of 1 half. So when k equals 2e to the power of 1 half, there is exactly one solution.
Okay, that makes a lot more sense. What about problem 5?
I immediately recognized that the question was asking for the tangent line of sine 3 plus x to the power of 2 when x equals 0. I found the derivative of sine 3 plus x to the power of 2, which is cosine 3 plus x to the power of 2 times 2x plus 6. Because we are finding the tangent line when x equals 0, I plugged in 0 and got 6 times cosine 9.
That's weird. I got undefined because I put the equation into the Desmos, and at 0, the left side of the equation goes to infinity, and the right side goes to negative infinity. So the two sides of the limit cannot possibly equal each other. So the limit can't exist.
Oh yeah, I got that too when I first checked my work in Desmos, and I was confused. But it's because you don't add parentheses around the 3 plus x to the power of 2 when then Desmos thinks you're squaring sine instead of 3 plus x.
Oh, yeah, I see. Thank you.
Problem 6 took so long for me, I had to redo it many times.
Yeah, I couldn't get it at first either.
I never figured it out. You guys did it?
Yeah, so basically it's another induction problem. It's just a way more complicated equation. Just like with problem 2, the first thing I did was solve for when n is equal to 1. I did this by taking the first derivative of the left side, since that's when n equals 1, and I set it equal to the right side at n equals 1.
Yeah, I did that too. The next thing I did was expand off the right side of the equation. Since there's an e to the power of ax on both sides, you can just ignore that term. So I only had r sine bx plus theta to expand. I did this by using the sum formula. So I got r cosine theta times sine b of x plus r sine theta times cosine bx.
Yeah, I got to that point. I just didn't know what to do after that.
After that step is when it gets really complicated, and you had to use the other information the problem gave you, like r squared is equal to a squared plus b squared, and theta is equal to arctangent of b over a. First, you should remember that right now we're only dealing with the right side of the equation when n is equal to 1. Since we're using induction, we need to prove that this right side of the equation is equal to the left side. And again, we can forget about the e to the ax term since it's on both sides of the equation. We need to get r cosine theta times sine b of x plus r sine theta times cosine b of x equal to a times sine of b of x plus b times cosine of b of x. As you can see, this means we need to get r cosine theta equal to a and r sine of theta equal to b. To do this, we use the r squared is equal to a squared plus b squared that the problem stated in the beginning. We can put this on a right triangle, where r, the hypotenuse, is the square root of a squared plus b squared. This means the two legs are a and b. If we set the angle theta in between the hypotenuse and leg a, we can use the other piece of information given to us at the beginning of the problem, where theta is equal to arctangent of b over a, to solve for theta. Because of our right triangle, we can use basic trig identities to say tangent of theta is equal to b over a. Then we can take the arctangent of both sides to cancel out the tangent. This would give us theta is equal to arctangent of b over a, which explains what was given to us at the start of the problem.
Okay, wait. So right now we're finding what theta is equal to, in order to plug that into sine theta and cosine theta, so we can find sine theta and cosine theta and prove that r cosine theta times sine dx plus r sine theta times cosine dx equals a sine dx plus b cosine dx?
Yes, exactly. So we can use the right triangle we set up to find cosine and sine as well as tangent. Using SOHCAHTOA, we get cosine of theta is equal to a over the square root of a squared plus b squared. Since we know theta is equal to arctangent of b over a, we can plug theta into cosine theta and get cosine of theta is equal to cosine of arctangent of b over a, which equals a over the square root of a squared plus b squared. Remember, like you said, we want r cosine theta to equal a. So we take what we know r is and what we know cosine theta to be and plug it in. We get r cosine theta is equal to the square root of a squared plus b squared times a over the square root of a squared plus b squared. This simplifies to r cosine theta is equal to a, which is good because that's what we wanted to prove. We can then do the exact same thing with sine of theta. Using the right triangle, sine of theta is equal to sine of arctangent of b over a, which is equal to b over the square root of a squared plus b squared. We plug this in for r sine of theta, and that gets us r sine of theta is equal to b, and we have proven that the equation works for n equals 1, which was the first step of induction.
The next step would be to prove that the statement works for n plus 1. We do this by plugging in n plus 1 for n.
No, you can't just plug in n plus 1. You have to take the first derivative of both sides so that you get n plus 1 for the variable instead of just n. After you do that, you should expand out the right side of the equation the same way you did for n equals 1. Except now you're expanding r to the n plus 1 times sine of bx plus n theta plus theta, instead of r times sine of bx plus theta. Once you've expanded it, you should get is equal to r to the n plus 1 times sine of bx plus n theta times cosine of theta plus r to the n plus 1 times cosine of bx plus n theta times sine of theta. You can solve for cosine of theta and sine of theta using the same triangle from earlier, except now you're calling the hypotenuse r and not square root of a squared plus b squared, since they are equal. you should get cosine of theta is equal to a over r and sine of theta is equal to b over r. Once you plug those back into the equation, the r in the denominator cancels out with the r to the n plus 1 in the numerator, leaving you with just r to the n times a and r to the n times b. Now, if you go back and take the first derivative of the equation when n is equal to n and not 1, and you simplify the right side, you should get r to the n times e to the ax times a times sine of bx plus n theta plus b cosine of bx plus n theta. Remember in the last step, we proved that that's equal to r times sine of bx plus n theta plus theta. So we can plug that in and get e to the ax times r to the n plus 1 times sine of bx plus 1 of n plus 1 times theta. This is what we are trying to prove, that this equation works for n plus 1.
I see. Since you proved that when n equals 1, the equation is true, and if you assume that the equation is true for n, the equation must also be true for n plus 1, which you just showed. That means that the statement must be true for all positive integers n by the principle of mathematical induction.
Yes, exactly.
Did anyone look at the last problem? I concluded that 2 actually equals 1.
Yeah, I was confused too, but after looking at it, I realized that they made a mistake. When they took the derivative of x plus so on x times, they didn't take the derivative of the number of x's, so it was solved wrong.
Oh, that makes more sense. Okay, guys, I think I have to go to class now, but I'll see you tomorrow.
Okay, bye.
Me too, bye.
Bye.